Hi there. In this video, we're going to talk about random variables. A binomial random variable represents a situation with two binary outcomes. For example, if we toss a coin, we have two outcomes, either a head or a tail. Or if we have a survey with a question and the answer to the question is yes or no. Another example is the roll of a dice. We could get either a 6 or not a 6. The point is that binomial random variables are an extremely powerful modeling tool because anything that we can put into two independent groups can be modeled using a binomial random variable. It all depends on how we define what the random variable represents. So we can have a number of experiments or trials. In this case, the random variable x represents the number of times a particular result happens for n number of trials. For example, if we toss a coin, then x could be the number of heads that happens if we toss the coin a certain number of times. Let's just say we toss a coin 4 times, and the random variable x represents getting 2 heads. So if you have 4 trials with x equal to 2, so in total, you have 6 outcomes, which are different combinations of getting 2 heads and 2 tails. Since we are assuming each trial is independent, the probability of getting a head the first time is 0.5. Then the probability of getting a head the second time is 0.5 as well. However, we want 2 heads from this set of 4. So the third toss of the coin is the probability of getting a tail, which is 1 minus 0.5. And then the final toss is then also getting a tail, which is probability 1 minus 0.5. So this is the same as writing 0.5 squared into 1 minus 0.5 to the power 2. The first exponent 2 represents the number of heads, and the second exponent 2 represents the number of tails. We then need to multiply this result by the number 6, since there are 6 combinations. So please watch my last video on the difference between permutations and combinations to understand what is the difference and to understand how we are using 6 in this particular scenario. So this resulting equation that we have just shown here, it corresponds to the probability of getting 2 heads if we toss a coin 4 times. We can then generalize this, and we generalize it by saying that the probability of the random variable x taking on a certain number of results, which we designate by the small letter I, which in this case was the number of heads, then we'll have n choose I, that's the first term, which is the number of combinations, and then multiplied by the probability of getting the number of heads, which is p, and this is now to the power I, and all this is multiplied by 1 minus that probability to the power n minus I. And if we compare that above, we can see that I was the number of heads and n minus I was the number of tails. So this formula would be applied for all values of I that are valid. So in this case, it would be 0, 1, 2, all the way to n, which is the number of trials or experiments. So what we're going to do now is look at an example of how we can model a real situation using binomial random variables. Imagine you are taking a 10-question multiple choice test where each question has 4 options A, B, C, D, and you don't know any of the answers. So what you do is you randomly guess for every question. So let x be a binomial random variable that represents the number of questions that you answer correctly. N equals 10 represents the number of trials, or the fact that there are 10 questions in total. And since there is 1 in 4 chance of getting a question correct, that means that p is equal to 0.25. We can then apply the general formula for different values of x. So I will go between 0 and 10, where x represents the number of times we get a question correct. So let's do that. So since there are only 10 questions, x will take on the value between 0 and 10 as we have just shown. So if x is equal to 4, it means that there are 4 correct answers. We can then compute the probability of getting an x number of questions correct, which is what we have just shown in the table. So we can see in the left column, or the first column, we have the different values of x going between 0 and 10, and that represents the number of questions that we got correct. And the second column, or the column on the right, is the actual probability that we have worked out using the formula that is displayed on the screen. We can then plot these two columns, and we can plot the number of correct answers on the x-axis and the corresponding probability on the y-axis. We can see that the largest probability occurs at x is equal to 2. So this means that if we randomly guess all of the answers in a multiple choice test, it's likely we'll get, or most likely that we'll get 20% or 2 out of 10. Following on from this, what we can do now is plot a cumulative probability distribution. So it looks like the graph that has just been displayed. And how we plot it is by summing up the different probabilities up to a certain value of x. So let's just say we ask ourselves, what is the probability of getting less than 6 correct? So what we would do is we would sum up all the probabilities between 0 and 6, and then we would just plot it. And then we would do that for all the values of x. We would sum it up until that certain point and plot the values until we get this curve that has just been shown. So we can see from the plot that the curve flattens out at 6. So what that means is that we will probably never get a result that's more than 6 out of 10. So in general, we can model any situation using a binomial probability distribution, firstly by defining a random variable with binary outcomes and then plotting the probability distributions. Thank you very much for watching.